Hello everybody and welcome to this new video in which we will solve a complex equation. Before we start with the actual content of the video, I would like to thank you as usual for the support you show towards my channel and my whole project, and I invite you to continue to show this support, subscribing to my channel, hitting the bell button in order to stay always updated with new videos and content in general. And also, if you want to support me, more closely, you can also donate via the links I will give you in the description of this video, like in every other video. So I've done my usual YouTube introduction. It's mandatory in YouTube, and now we can start with our video. So we want to solve the following equation. In C. So we are dealing with complex numbers. So we have this equation to solve. We have z squared, which multiplies z modulus squared minus 1 plus I, which also multiplies z star, which is nothing but a complex conjugate of z, and this whole expression is equal to 0. So we have to look closely to this equation, and we almost instantly recognize that we can exploit the definition of the modulus via the product between a complex number and its complex conjugate, in order to write the whole equation in an easier way, basically. So basically we remember that the modulus squared is equal to z, which multiplies z complex conjugated, no? Then we can rearrange the equation in the following way. We have z squared, which multiplies z times z star, and then minus 1 plus I, which multiplies z star, and this whole expression is equal to 0. Then now we cannot divide both members by z star, because otherwise we would lose a solution of our equation. But alternatively, we can basically factor out z star in the following way. We have z star, which multiplies, so we are factoring out this contribution here. Thus we can write z raised to the third power, okay, which is this product here, minus 1 plus I, and that's all, and this whole expression is equal to 0. So now we have an expression which is basically equivalent to the one we have started with, but it's much simpler. So now we know that one solution is of course z star equal to 0, but basically it corresponds to z equal to 0 because this is a banal real number, okay, very trivial real number, it's 0. This solves the equation by the product rule, but obviously, as we have said, this is a trivial solution. The really interesting part is inside the square bracket. Then we have to solve also this other equation. We have z raised to the third power and minus, it's minus, am I right? Yes, minus 1 plus I is equal to 0. And then, as we have seen in my previous video, This problem basically consists of extracting the nth root of a complex number. So we have to write z raised to the third power is equal to 1 plus I. Then we have to convert 1 plus I in its exponential form, because it will be easier to extract the nth power. So we have that we can write 1 plus I can be written as square root of 2, which multiplies e raised to I, should be pi over 4 exactly. And this is easily seen because we have that the modulus of this number is obviously 1 squared plus the imaginary part of 1 times I is again 1, and we have to take the square root of 1 squared plus 1 squared, which is 2 under the square root, okay? And then theta is equal to the arctangent of 1, which is pi over 4. Okay, and this is our complex number in its exponential form, modulus and phase e raised to I pi over 4. Then now we can proceed to rewrite also z raised to the third power in its complex form, in its exponential form, because if z is equal to rho times e raised to I, let's call it phi, okay, then z raised to the third power is nothing but rho raised to the third power, which multiplies e raised to I 3 phi, and then we can equate the left hand side of the equation with the right hand side. So we have rho raised to the third power, which multiplies e raised to I 3 phi, and this is equal to square root of 2, which multiplies e raised to I pi over 4. And then we are almost done, because now we have to equate the modulus with the other modulus and the phase with the other phase. But we have to remember that obviously, since we can convert the complex exponential in its trigonometric form, we have to remember that our solution will be periodic with a period determined by this product here. So we have that rho to the third power is equal to 2 under the square root, which is equal to 2 raised to 1 over 2. Then rho is equal to 2 raised to 1 over 6, because we have to take the third root of both sides, okay? And then we have that how did I call it, phi. We have that 3 phi, and now I will explicitly write the dependence from the periodicity with this subscript k here is equal to pi over 4 plus 2k pi, and we have to remember that k goes from 0 to we extracted the third root, so we have 0, 1 and 2. Yeah, perfect. Okay, so I can write that phi is equal to pi over 12 plus 2k pi over 3. Perfect. Again, with k ranging from 0 to 2. So our solution are z equal to 0, and then we have z, k, and these are actually three distinct solutions, which are given by 2 raised to 1 over 6, which multiplies e raised to I phi k, with phi k given as pi over 12 plus 2k pi over 3, with k ranging from 1 to 2. Okay, and with this writing here, I would like to close this video. We have seen that basically extracting the nth root of a complex number is equivalent to writing the whole thing as a complex exponential, because it really simplifies the work we have to do. And I think we will see some other equation in the complex field, and then we will move on to more advanced topics. Okay, then I close here this video, and as usual I would like to thank you for your attention. Bye bye.